So I did this problem about a year ago, but we're redoing it today. Recently, a student pointed out a big mistake I made when finding the removal efficiency for BOD after biological treatment. So I want to make sure to redo this, get the concept right, and get the right answer. So before going through the calculations for this, we're looking at primary and biological treatment. Before this, let's cover the basic concepts similar to the old video that we had. So we have a wastewater treatment process because it says in the problem statement we have primary and biological treatment. When we have both of these, the overall treatment will be the wastewater treatment sequence. So in this case, we can break these down conceptually. We have a physical process where we have the preliminary treatment and primary treatment. We have the biological process. This is the secondary treatment. Biological treatment is always secondary treatment. And lastly, we can call the last process a chemical process, tertiary treatment, where we have our disinfection. Breaking these down, we know there are several sequential steps here to remove contaminants from the wastewater or from that raw water coming in. So the first one is the bar racks, and this is what we call the screening. We do this through these large metal screens right here where we have our bar racks. And at the end, what we're doing is removing large debris such as sticks, leaves, and other solid waste to prevent clogging in our downstream equipment when we remove these. Those are the bar racks. Then we have our important grit chamber right here. That's what's shown here. We get some grit coming out as shown. And we know this is after screening. So that water goes into the grit chamber. Here we have the sand, gravel, and other, keyword here, heavy particles settle to the bottom due to gravity. It's the heavy stuff, gravel, sand, the heavy ones that can easily settle due to gravity. So we know these are going to be denser particles that settle out faster than organic materials, making them easy to remove. Grit removal helps protect mechanical equipment and prevent further sediment buildup. That's the grit chamber. Now, the primary clarifier, the very important, and this is the sedimentation basin as well. It can be called a primary clarifier or a sedimentation basin. And notice here we have sludge coming out. We have sludge always from that primary clarifier sedimentation basin. So we know in this case, we take the suspended solids. Keyword right here. What's important is the suspended solids. So these are the particles that are suspended or in suspension in water. They're floating in water. They're suspended, they're in suspension. So these solids settle to the bottom to form sludge. This sludge is periodically removed for further processing, and any oils or grease that rise to the surface in that sedimentation tank or primary clarifier are going to be skimmed off. Maybe you've seen that in real life. I know in my university days, we went to the treatment plant and we saw that in action. So we do skim off that grease or oil that builds up at the top. And we know this step reduces the organic load before the biological treatment. That's the primary clarifier. Then after that, we move out of the physical process. We go into the biological treatment. Very important right here, secondary treatment. Notice it consists of the aeration tank and secondary clarifier. With that said, let's talk about the aeration tank. So we know in this tank, wastewater undergoes biological treatment to remove dissolved organic matter. Dissolved organic matter. Aerobic bacteria are introduced and given oxygen through mechanical aeration, allowing them to break down organic pollutants. So aerobic means we need oxygen. The bacteria, the microorganisms need oxygen. So they need that oxygen to eat up that organic pollutant or that BOD. So they eat up the pollutant, they need more oxygen. So we need to continuously supply these bacteria with oxygen. Aerobic respiration is what we have to allow them to break down the organic pollutant efficiently. So that's what we see here. We do the supply of air through mechanical means in that case for the microorganisms in the aeration tank. So this is important in reducing the biochemical oxygen demand, the biological oxygen demand, BOD, and the nutrient levels in the water. So it helps us reduce the BOD, which is what we want to do, and also reduce the nutrients such as nitrogen and phosphorus when we do the aeration tank. So now the BOD, I want to define that a little bit similar to what I did that we talked about in the last video. We can discuss that down here just to know the exact definition of this. BOD, biochemical oxygen demand, or sometimes you see as biological oxygen demand. BOD is a measure of the amount of oxygen required by aerobic, they need oxygen to break down organic matter in water over a specified period, typically 5 days at standard 20 degrees Celsius. So it's an important indicator of water quality, particularly in wastewater treatment, as it reflects the degree of organic pollution. So what's going on here? These are the major things we should know about microbial respiration. Microorganisms consume the organic materials, this is the pollutant, as food. So they eat the pollutant as food. But in the same time, they use oxygen. They need oxygen. Similar to us, in order for us to get energy, to have an energy output, we need that oxygen. In this case, in order for the microorganisms to eat the organic or consume the pollutant organic materials, they need oxygen to ensure the process of aerobic respiration. And the more organic material that's present, the more oxygen they're required to break it down. There is an oxygen demand. So high BOD levels will indicate a high concentration of organic matter, meaning more oxygen is required by the microorganisms to decompose these substances. This demand for oxygen can strain available dissolved oxygen in water, especially in natural bodies like rivers, lakes, potentially harming aquatic life. And if we look at this image here, that's really what this is showing us. Let's say you have the water right here. The black dots are the BOD, and think of this as the pollutant. The white dots are the oxygen. So now, BOD, organic matter, is present in water. Let's say in that raw water or that water that comes out after primary settlement, primary treatment. So then we know the BOD is going to be the food for the microorganisms, as we talked about. So to eat that food for these more microorganisms, to eat that BOD, the black stuff, they will have to use the oxygen. This, let's say microorganism, is going to use up that oxygen. So the microorganisms use oxygen when they consume BOD. This depletes oxygen levels over time. There is that correlation, as we said here, that high BOD levels indicate a high concentration of organic matter, meaning the microorganism need more oxygen. So last thing here is wastewater treatment in the aeration tank of the plant. BOD reduction is the primary goal when we have the secondary treatment. Most importantly, by supplying oxygen to the wastewater, we know treatment plants support the aerobic breakdown of organics by bacteria, thus lowering the BOD. Reduced BOD in the effluent indicates that much of the organic load has been processed, making the water safer for the release into the environment. At the end, in summary, BOD is directly related to the amount of oxygen that microorganisms will consume as they degrade the organic material. Lowering BOD through treatment is essential to preserve oxygen levels for aquatic ecosystems and ensure water quality. That is BOD, know the concept behind that. So that was discussed in aeration. Last two right here. So we have after aeration, the secondary clarifier. This still acts like a primary clarifier, but we do this here in the biological process. So in this case, we have the after biological treatment, after the aeration tank, the water flows into the secondary clarifier. We have the microbial biomass, or the activated sludge, settles to the bottom, separating from the treated water. So we still have sludge here settling to the bottom. And in this case, we know some of the settled biomass is returned to the aeration tank to maintain bacterial populations. So what we do here is return some of that sludge as shown, this is the return activated sludge, to ensure a population of microorganisms that continue to do their job breaking down the pollutant and the organic matter. We still need to return some fresh, highly active return activated sludge. Not all of it, not all the one that comes out here at the bottom, but some. We still return some as shown. Then the remaining is going to be wasted, and we treat that through the sludge beds and also other treatment processes. So that's going to be the one right here, and that is returned, and the excess is removed as waste sludge. And finally, disinfection is the last one here. We can have UV, chlorine, and also ozone as well. So the clarified water undergoes disinfection to eliminate any remaining pathogens. Keyword right here, we're treating the pathogens. We can use chlorine, ultraviolet UV light, or ozone. Disinfection ensures that the treated effluent is safe to release into the environment or reuse. That is the key concept in this case for the wastewater treatment train. And to solve this question, a hint for you is use that keyword incineration in this case. This will give us the removal efficiency. We often deal with this formula, especially in water treatment, wastewater, environmental. So whatever comes in, we subtract that minus out divided by in times 100 gives us the removal efficiency. That's what we will do. It's the removal keyword right there, removal efficiency. So based on this problem, let's start with the primary settling. Notice we have after primary settling, we have the data here for each parameter. And after biological treatment, we have the data. The raw water that comes in, which is going to be this one, was given as well in that data here. So primary settlement, the removal efficiency for BOD is most nearly what? What did you get? You can pause the video, see if you get an answer from these. Most nearly. So we will use that formula that we saw below. You can find that in your PDF in the handbook. So the removal efficiency, I'll just call it removal, right here. We take whatever comes in, minus out, divided by in. That's all we do in this case. Don't forget to multiply that by 100 to get it in percent. So whatever comes in now, primary is the key word here. After primary, whatever comes in based on that BOD, this is the one we want to focus on, is this biochemical, biological oxygen demand, BOD, is this. This is in, so it should be 210. That comes in, minus after primary, this is what comes out, 120. And then we do divided by whatever comes in, which is 210. And we multiply that by 100. So that will give us the answer. What do you get there? 210 minus the 120 divided by 210. And we multiply that by 100. We get about the 0.42 or 43. So it's about 43%. It's 42.8. So that would be closest to 43%. And that right there should be our most nearly answer. So it's about 43% removal efficiency. Note what we're visualizing here. This is what comes in. This is the 210. And here is the primary. This is what comes out. And we said that was the 120. That's what comes out here. So out is here. This is in. And really, we're just isolating this. Imagine like drawing a box around this. That's what comes in. This is what comes out after that primary. And then we do the calculation. That's for that one. Now let's go to the next one. That one is much trickier. After biological treatment, the removal efficiency of BOD is most nearly what? What did you get for this one? So we know removal. We're talking about removal efficiency in percent. We take again the in minus out divided by in times 100. Now what did you get for the in this case? So we know biological treatment, we have to always remember it's the aeration tank and the secondary clarifier, keeping it simple. So what we can do is draw a box around that. It's this. This is, let's say, our system. Now we have the thing that comes in is this, right? Do not use the raw water because that raw water comes in into the primary treatment. This really, we can call that primary treatment. So in this particular case, it's not the raw water that comes in. What comes in is what leaves this system, which is the preliminary and primary treatment, which is the value that we get here after the primary clarifier. And it's really, in this particular case, to be precise, it's going to be the value of the 120. The 120 in this one should be the one that comes in. This comes in, and this is going to be the one that leaves. So this would be the out. That's the trickiest thing about this, and that's where I made my mistake. So what comes in here is the 120 into that secondary biological. What comes out is going to be the 30 right here, and that's what we will plug in. So we take the 120 minus the 30 divided by 120 and multiply this by 100. What do we get for this one? 120 minus 30 divided by 120. So we get exactly 75%. Is that what you got too? Or maybe you got a different answer. That's still one of these tricky questions right here, but it should be B for this one.